So I also asked you guys to read chapter 3 and 4. Last week and the week before we were discussing performance analysis, and then we start discussing performance measurement. But for the performance measurement, it was a bit simpler than the analysis, right? What was the most important stuff in the performance analysis? What was the main thing that I asked you like 10 times, 20 times in class? 뭐지? If you cannot remember anything from those stuff, only thing you should remember is definitions of different notations. If you do that, then I think you'll be okay. You will have questions to dealing with those complexity and more. They probably give you setup code, pseudocode, and ask you to analyze the maximum, asymptotic complexity of certain in a piece of code. So after that, we were discussing actually measuring the time, the ticks, CPU cycles. What was the CPU cycles, and what was the another main factor when we measuring the performance of a program? I think it was on the memory part. Certain programs access memory a lot, the other programs maybe not. Other than the algorithmic complexity, the memory access patterns also have a huge impact on the actual measurement of a code. So we discussed very simple way of doing this, and then we get the beginning time of a algorithm, and then we put whatever we wanted to do, maybe any sorting algorithm you choose to do it, and then put it in, and when you're done your sorting or any program that you choose to use, done, get the time of the finish, and then you simply subtract from finish time to from start. Not good. 커피를 좀 마시고 들어왔었어야 되는데. From finish time to start time, and then you will have it. And what was the potential problem of all this? Measuring all this. What was the potential problem of measuring all these? And they probably ask you to read a couple of programs in your textbook, couple of examples that try to explain it, and you will see one table says all 0 for that measurement part, because maybe it's just too fast to measure in some cases. Even though they have a difference in it, the actual number is just too small, everything else will be displayed as a 0. That's not the case. That's why they have a certain range of numbers like plus minus 100, those are stuff. So they keep, another suggestion they have in your textbook is probably asking you to do this multiple times, like 1,000 times, until you get a reasonable average numbers, so you can determine the actual measurement. You can actually determine the performance of a algorithm in terms of time or cycles, right? 그죠? No? Yes? No? Hopefully that's what we discussed last week. 맞아? Hope so. So I'm sure that most of you already read all of this, chapter 4. Assignment 1 is just asking questions from 1 and 2, right? 어저께 올렸으니까 I understand. 1 and 2. Assignment 2 might be a bit tougher than assignment 1. So you still have time to cover chapter 3 and 4 till next week. Okay? So if you're thinking you're a bit behind, then don't worry too much about it. And I remember someone asked me about the reading a textbook. Again, I'm not expecting that you guys to read from the first word to the last word in all the chapters. No. I know you guys are busy, so if you don't have too much time, then try to read some of the examples they say in the slide first. So do not try the first line of the chapter 1, and that way it will make you bored soon enough. So, or maybe if you read those examples programs, usually at the paragraph right below the figures explain what they try to say. So that's probably good enough for now. Of course, you will have to find the certain sections in order to complete your assignment, but usually they are overlapping. So you should be okay. 너무 책 많이 읽는 거에 스트레스 받지 마요. 지금은 너무 많으니까 읽으라는 것부터 읽으면 그 읽으라는 게 중요한 거니까 대부분 그런 커버가 돼요. 뭐 이 챕터는 무엇을 설명하고 그런 거는 뭐 대충 안 읽어도 되니까. Okay? That was brief answer to some of your questions, and then we covered this last time, blah, blah, blah. And I also ask you to read exercise 4.1. They usually do it, and there was some reasonings for why not. We're not focusing too much on this space complexity stuff, right? Page 122, page 123 has those answers to it. I explained it last class as well. So you should be able to find it and read it on yourself. Okay? That was brief review on the last class. We also, I kind of skipped through some of the slides last class as well, but we're gonna go into array representations, arrays that we already know, but let's say that we try to implement our own array in different ways. Then what kind of choices that you have, probably? Array is what? Well, just a series of numbers, number by numbers, next number is what? So there might be a multiple way of representing that. And that array itself is like you can express them in terms of data object. What is data object? It's some of the definitions. I'm going to read it first and I'll let you know. Data object, a set of instances or values, numbers 1, 2, 3, 4. 0, 1, 2, 3, 4. Boolean is also a instance, a value, true or false. 그죠? Letters, A, B, C, D, D, F, G, letters. Strings, what might be the right definition for strings? I don't know, there can be many, but it seems to be a set of letters in sequence. If you put a single letters by sequence, one by one, next to it, then it's probably describing a string. So each characters have their own meanings, which if they have a very primitive meanings, I mean, how can you define numbers 1 to 9, 1, 9? How do you define 1? I mean, those things are primitive. It's already defined. We already know. But if you start putting those numbers in a sequence in different combinations, how would you represent them? So those are the data object. Individual instances, either primitive or compositive. Composite. If you want to think easily, single character or maybe a set of characters. But we like to give them a meanings, and we like to find a way to represent those meanings into a data structures. Elements is the individual components of a composite instance. So definitions are theirs, and in the textbook they probably try to give you some definitions on primitive. I mean, those things are basic, you can read it through. So we kind of know those things are data object. I mean, these things are now data object. Things that we use in the programming too, right? I mean, those are the basic requirement to write a program. When you're writing a program in C, do you need to define a number? 1, 2, 3, 4. If I write a 1, 2, 3, 4, the program knows that those are numbers, right? I don't need to define it myself. So then it's a primitive. Those things are primitive. Data structure is simple as this. Data object together with the relationship among instances and elements that comprise an instances. Whatever that means. It's a lot of definition of definitions. Simply is this. Number 3, 6, 9. If you count them as a single number, it doesn't mean anything. But if you try to write them in a sequence, 6, 3, 6, 9, we often recognize them as 369, right? We just give them we treat them as a data object. It's a huge number from that point on. Or we can interpret in different ways. If you count 369 as a single character, like the letters, then is it same as 369? It has a different meanings. 그죠? 레터로 봤을 때랑 these two have two different meanings. This one, 369 numbers, large numbers. This one, just set of characters, 3, 6, 9, side by side. Two different meanings, two different data objects. You can interpret differently. So this means they have a relationship to each other. This one, if 3 is in front of the two numbers, then we can multiply them by 100. 3 times 100, 6 times 10, plus 9 times 1. Relationship to describe this number. This one, not a number, characters. Among instances of integers, 369 is less than 370. Is this possible inequality that you can say? If we interpret them as a characters, is that possible? 369 캐릭터로만 보면 370보다 작다고 얘기할 수 있어요? No, right? We can say those relationships because we treat them as integers, numbers. Also, as well as a summation and some addition, not summation, addition and equality signs as well. This relationship is possible because we treat them as numbers. But maybe in C programming, what if I start putting a quotation here and here? Then we'll be treating them as a sequence of characters. It doesn't mean numbers anymore. Among elements that comprise an instance 369, that is an instance that we have, 3 is more significant than 6 because it's in front of it. 3 is immediately to the left of 6. 9 is immediately right of 6. Those are numbers. So they try to do this. And a simple example on the data object. 내가 요즘 왜 이렇게 버벅대는지 이유를 찾았어. 방이 너무 더워. 여름에 그래도 에어컨이 있어도 되는데 버벅대. Plus, we have a Thanksgiving in Wednesday. I'm a bit excited. Before I forget, some people already told me they are going home for Tuesday. 아니다, that's okay. Wednesday. 아니다, not this class. 상관없지, 여기. I will ask you in database class. Abstract data type, ADT. Abstract data types. Another definition that you should know. I mean, very easy question to be asked in the exam situations, but surprisingly, I give you this as a bonus questions. A lot of people got it wrong and define their own way of ADT. ADT is collection of the data and set of operations that can be performed on the data. Data structure is there to describe a certain data. Because we have a data structure in certain format, we can build other functions to work with those data structures. That's what it means. ADT is collection of the data and set of operations that I can use those data. Let's say data is integer numbers that we just saw in the previous slide, 3, 6, 9. What might be the set of operations that I can perform on the integers? What might be the easy set of operations that I can do? Addition, subtraction, multiplication. Those are set of operations that I can perform on the integers. So I already, my data set is integer, and set of operation is those arithmetic operations. But integers, again, we don't have to define the integers in most of the languages because it's already predefined. What if you like to have your own data object and like to define your own operations? And that's a concept of ADT, and it's a key concept in data structure. It enables us to think abstractly about data. I don't know. When you see an integer, it's not an integer anymore. According to your own ADTs, I mean, anything is possible. So we can separate concept from implementations. Right. You will see a set of operations in like coding ways, and you usually don't care what's written inside of each operations. I mean, unless you define it on your own, that's what it means. And if you need to change some ways of doing that operation, then you can just simply change some of the implementation inside of each operation, not entire structures. Typically, we choose a data structure and algorithm that provide the implementation of the ADTs. Typically, we don't write ourselves. There are already the good defined ones that we can use. That's why we discussed briefly on inheritance and stuff like that. Public, private. Those are, classes that we also study. Similar concept is defined. Let's take a look what it means. List is our first things to look at. What is a list, linear list? Of course, they already give you definitions, but what is a list, linear list? Whoa. Someone please read it out, I don't care. Linear list is a data object whose instances are of the form of E1, E2, En. Some objects, whatever instances is next to each other, one by one. And you have this list, that form. EI is an element of a list. You can define anything. If you like to have an integer list, then element is an integer. If you like to have a character list, then each element is a character. What else? You could have a list of list. List of list. So each element of that list of list is list. So you might have a set of list inside a list. E1 is the first element. En is the last element. N is the length of the list. How many elements do I have in my list? N, usually we like to use this N as a, when we're doing the performance analysis, right? We like to see it. When N is 0, it is called the empty list. What is empty? Nothing there. So if you ask for the length of the list, if it's empty, what might be the returning value? Simply 0. Simply 0. E1 comes before E2, E2 comes before E3, and so on. So you could say E1, and next number is E1 plus 1, E1 plus 2. So the numbers keep increasing. Those index values increasing. That is a definition of having a list like this. Examples: student names ordered by their alphabets. A list of exam scores sorted by descending orders. descending order는 뭐야? 제일 못한 사람부터 나오는 거네. 그죠? 아니구나. 제일 잘하는 사람부터 나오는구나. I'm sorry. 제일 잘하는 사람부터. Yeah. The biggest one first in the list, and if you go down, that lower marks will be shown. So I guess in order to do some type of sorting, you need to have a list first, I guess, right? So this is ADT for the linear list. It's very similar to the code C++ when they explain OOPs and stuff. Let's take a look. Abstract data type linear list. Someone already defined it. Instances are ordered finite collection of zeros or more elements. And now this is their instances. Now they define the operations, set of operations you can perform on top of these data types. Operations, create an empty linear list. Easy, I mean, very easy to see. The name speaks itself. Destroy, erase a list. How do you erase a list? Or how do you create a list in the first place? I need to write down the actual code later. How do you create a list? I mean, what do you have to do if you wanted to create something in your programs? Create something in your program means you need to allocate some memories in order to write something on that certain memory part. So I create a memory space for my purpose. Destroy, delete that memory space that I wanted to use. Maybe I've done using this list. Is empty. It's a simple questionnaire, question function. So given a list, I like to know whether that list is empty or not. Why do you check whether your list is empty or not? What might be the possible cases? In what cases do you ask your list whether you're empty or not? If you wanted to add something into the list, if it's empty, I can just simply add it in. If it's not added in, then maybe I need to check whether that list is full or not. Something like that. Those things, anything is possible. Any situations. Length, return the size of the list size. So simply means we know the n is representing the list. So they probably return in the n, integer n. Find, return the kth elements of the list in a way. Return the kth element of the list in X. We'll see what that means. So they try to find a certain things, whether they exist in the list. Search for X, return the position of X in the list. How do I write a list? Typical way of indexing this is 0, 1, 2, 3, 4, 5, 6, 7. Let's say this is list, I don't know, list L. If I wanted to see something like that, list L dot maybe search X. What is it returning? Maybe X is in here. They search through the list. When they find an X, they're returning the index 5. So returning value will be 5. They define their operations they like to have. Sometimes you'll be using some of the functions inside of other functions, other operations. Deleting it, I mean, kth element, delete the kth element. Insert kth element. Insert X just after kth element. Insert X in the kth elements. Let's see, kth element maybe, kth is 3. Insert X, well, insert L dot, insert X, insert K, let's put K as 3X. Should be like this. Insert X after kth elements. Kth elements is, kth element is 1, 2, 3. Kth elements. Right next to the kth element, so it should be here. I'm sorry. It should be here. So we can take a look at it. I mean, definitions. I don't know why they need that operations, but somehow they need it. So you can use it. What if I ask you to write a code for each one of the functions in the exam situations? What can you do? If you think about it, it's just simple for loop, one for loop. You have an X, maybe for the search, you have an X begin with, you compare it to the position 0 element, compare it to the position 1 element, until you find an x. When you find an x, break the loop, returning the value of that index. So even if you try to write that code in a couple of more lines, the C code. So I probably will ask you to write your own ADT, not own, but some of the operations. I probably will ask you in the exam, whether it's a midterm or finals. Hopefully I give you the descriptions of the operations that I wanted to see. Output, out. Put the list into output stream out. What happens if you execute these operations? 뭐야? 저거 하면 어떻게 돼? List output 하면 어떻게 돼? They just simply print out the content of a list into your maybe screen, streaming out. How do you print out the list of this? How do you print out the every element in this list? For loop이지 뭐. Simple for loop. One for loop, print everything. Print index 0, 1, 2, 3. I hope you can see it. I mean, if you still wanted to go back to the integer example, then you will have instances will be a integer operation for addition, bracket, subtraction, bracket. What else? Multiplication, bracket, division, bracket. Those are the operations that you try to define. So this is ADT for linear list. You will see a very similar list for each data type. I mean, next chapter when they talk about other structures, they will probably show a very similar looking operations. I mean, create, destroy is the basic ones that you can use. I mean, but each type of data structures, they will have their own unique operations to perform. Might have a different name. They might not call it as addition. They probably call it as I don't know, insert. If they don't probably call it as delete, they probably call it as a pop in case of stacks. So, but they will share a very similar idea. Good thing about those ADT, if you know how to use that, how to write them, then after that it's quite easy. I mean, it's basically I will ask you how to use those operations to do something. In very limited cases, I will ask you to how to implement each operations, but most of the cases I will ask you for how do you use these ADTs to do something in your algorithms. If you know how to do something with your if you know how to use these operations, you don't need to know how they actually implemented inside. Implementation of the linear list, array-based, formula-based. So in order to implement that linear list that we discussed, ADT, we already defined ADTs, but there might be multiple ways of implementing that ADTs inside actual implementation. These are the options that you can choose. First thing, probably most easiest thing, you can use array to implement a linear list. Which one to use will have an impact on how to implement each operations. Whether you use an array, whether you use a linked list, you will have to implement differently for each operation they define in the ADT. We define ADT in terms of what they do. We didn't discuss too much how you can actually implement. Separation from the implementations. What is array-based? Use a mathematical formula to determine where, for example, memory address. I mean, bottom line is we try to write everything into memory, otherwise your computer not working. To store each element in the list, you already seen array-based here. Arrays. How do you define arrays in any program that you use? A, 10. I just define the array name A, have a 10 spaces for integer values. Array based. I could use this to implement a linear list. But how do you find my location of the elements? Maybe I can use a simple formula. What might be the formula that I use here? It's a very simple formula. I mean, we begin from 0, so you subtract minus 1 for every number. Position 1, the first number will be positioned at 0. 그죠? I minus 1. Position second number will be at position 1. So 2 minus 1, 1. Third number, 3 minus 1, 2. My simplest formula for this, I minus 1. This is ith element, for example. That's my formula to put the numbers in this into this array, and we're gonna use this array to implement a linear list. What about the others? Linked list. It says pointer based. Often I'll be referring to a figures, graphs, rather than discuss in this definitions. In that way, I usually draw here like this. We already have array. 뭐야? What can you do? What can you draw to represent a list? 아주 쉽게. Could have, maybe this is somewhere in my memory. I write my numbers. I might try to come up with the integer list. Maybe number 2. 4. I don't know, 5. Another way of representing a list. This one is array form. This one is using a pointer. I know where my next element is, which means I know where my next element's address is. So I simply point to that. Pointer based. Elements of a list may be stored in any arbitrary set of locations. Anywhere, it might be anywhere in your big memory. And each element has an explicit pointer or link to the next element. So I usually draw this way to memorize, rather than try to memorize the definition. No need to, for this one, no need to memorize. I mean, it speaks itself. What if I want to do one of the operation? Let's see. For example, I'd like to do this length operation in 2 different implementations. How do you do this for this array-based representation? Okay. Most cases, arrays have their own way of finding the total length. So I just simply use that function of the array to report the size of this array, and I use the same number for this length. Done. Very simple. What about this? How do I know that how many elements that I have in my list in the linked list representations? Let's say I'm going to add one more numbers in it. How do you know? This implementation was very simple. I mean, probably if I want to write it, my function length, if I'm using this array base, if I call this as a return a dot length. Done. 그죠? 이건 array based니까. array는 얼마가인지 처음부터 딱 나오니까. What about this? I can't use this here, right? So what do you do? 뭐라고? 다시. 그렇죠. You have a few different ways. Obviously, I cannot use the exact same implementation. So maybe I know where I start. So I just keep following. So I encounter first one. My count value is 1 here. I can see that I have a pointer to the next one. I go here. At this point, I can add 1. When I'm here, I know I have another point to the next one. It means I have a next value. Plus 1, 5, plus 1. When I'm here, I try to find out whether I have a next elements in my list. But they don't have any pointers. I can stop here. So 이거 못하면 죽어야지. 1 plus 1 plus 1 plus 1, 4. I do this implement in here. Just simply follow the pointers. Every time I advance, I add 1, add it up, and return it here. So the implementation will be different, right? Depends on which way that I do. What might be one of the advantages of using this linked list? Huh? Efficient memory, yeah. 그죠? For example, if I define a array 10 list, but I only have 4 elements to store, then I'll be wasting 6. 그죠? That's memory that I'm wasting. In this case, I have 4, I just have 4. I don't have any other waste. So in terms of memory space, it might be better. Later, in terms of operation as well, I mean, you try to add something, delete something. Sometimes this is a bit more efficient. In some cases, this is better, easier. So hopefully, as we go on, each chapters and each different implementation have their own advantages of doing it. So, and plus, at this point, I like you guys to see the difference for the point of having a separate implementation from abstract ADT. Array-based linked lists, these two probably mostly that we'll be using it. Indirect addressing, I'm going to read it first. The elements of the list may store in any arbitrary set of locations, same. Maintain a table such that ith table entry tells us where the ith elements is stored. Difference between the two, this one has a pointer to the next element. This one says they have a separate table to look it up. So my first element is here, my second element is here, my third element is, I don't know, here. They don't point at each other. So I had created another table. So first element, second element, third element, location, I don't know. Location of this is maybe 56. Second element, I don't know. That might be, 몰라, any arbitrary numbers that you wanted to see. 23. This location of this one is, I don't know, 16. So every time they like to find out where the second element, third is, they look at these tables to find out. Then I can go there and read numbers and use it. That's for indirect addressing. There are some other purposes of doing it too, but I'm going to skip it in this class anyways. Simulated pointers, similar to a linked list representation, but integers replace the C++ pointers. Instead of using the pointers, you could use the integer values to represent a pointer like. So do not worry about too much for this one. So I just wanted to, the textbook as well, I just want you guys to know there are different choices for the numbers. And the clear difference between these two might be one of the advantages might be a memory efficiency. Of course, there are plenty of other reasons that we use linked list in some cases, array in the other cases, stuff like that. 쉽지? 이것만 하면 뒤에는 계속 반복이야. ADT 뭐 다른 ADT에 따라서 나오는 거지. 계속 반복이야. array-based representation of a linear list, but I already explained most of the parts myself. It uses an array to store elements of a linear list. Individual element is located in the array using a mathematical formula. Simple mathematical formula that I already described. Location of I is I minus 1. First element, location is 0. Second element, 2 minus 1. Location is 1. 3 minus 1, 2. Very simple way of representing this. Ith elements of a list is in the position of I minus 1 of the arrays, because we usually keep track from 0 to the max n minus 1. Max size n minus 1. See figure 5.1 for different ways of store. Maybe I forgot which one it was, but they probably have a different formulas to store. Different formula to store. This formula somewhat related to the hash later, hash tables stuff. Template class 2. So this is 마이크 되지도 않는데 뭐하러 들고 있을까? So when you when you try to write this in class ways, I mean ADT, class, linear list, those functions that we will describe, delete, add, insert, those stuff will be in public functions. So anybody define this linear list will be able to use these operations because it's public. We discussed the concept of public and private. There are some other classes like protected and friends, but public, private, those things that you should know. Linear list, when I call that linear list, then I will create that list of size 10, for example. This delete function, delete a list elements. They probably call that as an element within the code. Boolean is empty. Integer, the returning value of the length is integer. They return the length of this ADT. These variables are defined as a private here, private length. If this is also public, then I could just simply ask them linear list dot length. But because those are private functions, I have to ask these numbers through the public functions like this. I have another set of functions to returning the value of each private values. Boolean find as well. Insert linear list t, delete linear list t, insert those the addresses of a position. Okay, that's for array-based ones. So now we're discussing this, actually not implementations, but the idea for array-based class. Let's discuss in terms of time complexity. What is a time complexity for creating a linear list in array? They already give you answers, but what is the time complexity? Why do they say time complexity of constant? Well, it's just simply define 10 numbers, you're done. You don't have any for loops. I like to create 10, size 10 array, done. That's constant operations. It's not going to grow that much. So each operation will have their own time complexity. Is search, or I forgot which one it was. Is search, if you guess, what might be the time complexity of search operation in this linear list, this linear list using arrays? What might be the maximum bound, upper bound? N. I mean, you have to go through the list array, the size of n. So maybe order n. Here, even though they say theta, it's almost same. I mean, theta is, you can say big O of constant 2, right? So when the slides say theta, it's okay for us to say order a big O of 1 constant. It's same thing. Doesn't really matter for us. Search and find. The next operation was a find. But this find is different from search that I just described. They give you the location of a element they wanted to look for. So if you know the location number, they simply look into it. So array에서 뭐 예를 들어 아까 전에 1, 2, 3, 4. The find operation will give you some number. Find position 2 and see whether that element X is there. So it's one operation, one lookup, because I already know the location. They already telling me to where to look it. So that's constant operation as well. So. Search, search, that what I just described. In order to search something into the array of size n, for example, the worst case, I need to look at all elements in the list. To be more exact, n minus 1 times. I need to n times. I need to look at all n elements in the list. So that's why they say big O of length. Well, if you have a difficulty again, they try to implement this algorithm, implement this operation here, but they simply use a one for loop. I mean, every time you advances within the array, they keep comparing to whether they have a value of x. You see a single loop. Easy guess is order of n, total length. But after this point, it's pretty much the same thing. They already give you the implementation details. They want you to determine the time complexity of each operations. Later, it will be important that whether you can implement such operation in smaller time complexity or not. It all depends on the performance part. Delete the kth elements if exist. Find the kth elements. So within this function, they need to delete the kth elements. So in order to delete something, what do you have to do first? You have to find it first. That's what they require. So within this delete function, delete operation, they use a find operation in it too. So it's perfectly okay to use other operations within some others. Okay. If I do that, then I don't have to write a find functionality within this one. 여기서 또 할 필요 없겠죠? 예를 들어 find operation에 전에 코드를 좀 잘못해놨으면 find 고치면 얘도 자동으로 고쳐지는 거지. 왜냐면 이 안에서 find를 썼으니까. 아니면 이 안에서 find 안 쓰고 하려면 또 똑같은 코드를 여기서 한 번 더 써줘야 되잖아. 그죠? Simple way of reducing the code too. Easier to when you encounter a bug, easier to fix. Time complexity of order length n minus ks, size of each elements. You can read it through. I mean, it's pretty much the same thing. I usually think of it as order of n max times. Insert as well. 이런 것만 설명하고 갈까? Throw out of bounds. I mean, the base algorithm is quite simple. You look into array to find it, but these are the some of the error signs. Throw out of bounds. What do? If k is less than 0, k is bigger than length is or, they say throw out of bound. What is the situation? Given value of k, what does out of bound mean here? We're still in the array-based representation. 뭐야? I have array size of 5, but number that I have in here, k, probably 6. It's outside of the boundary. It cannot have. It's bigger than, maybe it's bigger than total array size. I have only 5 elements, but they asking for 6 elements, which doesn't exist. So they checking for that part. 0보다 작으면 마이너스 1이면 말이 안 되지. Where is minus 1? 그죠? K is 5, but there is no 5. So they check it first. It's an error. Checking conditions and throws no memory. If length equals to maximum size, for example, like these, I mean, it's 5. You don't do any proper formulation. 여기서 다섯 번째 넣으라 했는데 뭐 꽉 차 있다든지 메모리가 남은 게 없다든지 그런 거 확인하는 거. 그래서 전체가 5개인데 5개를 더 뭐 5번째를 넣으려고 한다든지 그런 케이스들 checking. These are the actual part for the inserting elements. Well, inserting elements. How do you insert the elements? Elements array case equal x. 그렇게 하면 I just insert the elements into case. Let's if its k is 3, then x. 어떻게? This is elements. Name of this array is element 3 equal x. I just add it. 그죠? array는 이렇게 넣죠? add it. Output, I also explained it at the beginning. If you want to print out everything in your list, I equals start from 0 to less than the length. Every time element at 0 position print, element at 1 position print, 2, 3, until you hit the end of a list here. Of course, the time complexity is exactly n. You need to go through the n times. Bit more complex, you need to be a bit more careful than array-based because you allocate your own memories. And if you start allocating your own memory usage, then you make sure that you have to delete it as well. Pointer operation can be complex. Sometimes you lose a pointer. What happens when you lose a pointer in that example? Until 4 elements, I was doing fine, but I have another element to add. I made a mistake in my code. This one doesn't seem to be exist. What's happening then? Then you cannot recover. You have a broken list. So things like this are much more common than in this simple array-based ones. So you need to have a checking condition more careful of way of doing it. I mean, before even we're looking at the linked list ones, the pointer-based ones, how do you insert the elements in this linked list? Assuming I have a perfectly good 4 element list. 어떻게? The solution is very simple. I'm not asking you to code. It's draw something in this figure. Add. This is my new element. Maybe I do this way. I wanted to insert this new element right in the middle. I know so maybe I change this pointer to here. Update this previous pointer to here. Maybe changing just 2 simple pointers, I added new elements. In terms of addition, much more simpler and more dynamic compared to this array. What if you want to add this is completely full array, say A, B, C, D, E. But somehow I need to add a F to this array size of 5. What do you do? You can, right? So what do you do? 어떻게 하면 되겠어요? I create list of 6, array of 6, copy everything, and then add F. It's extra operations, copying, memory, much more. This one, changing just a pointers, I can add a new one. most of these stuff will be given in the figure ways as well. But if you just try to read the definitions, it's not clear. So I recommend you to draw it. I mean, you will have a bunch of more examples later to take a look at it. 좋지? 저게 훨씬 좋아 보이지? 그죠? 근데 나중에 가면 귀찮아요. 하다 보면 그냥 이걸로 하게 돼요. 체크할 게 많아갖고 귀찮아요. 링크리스트도 다 C++ 라이브러리 보면 다 돼 있어요. 그냥 가져다 쓰기만 하면 돼. ADT가 다 돼 있어. 링크리스트 ADT 찾아보면 템플릿 클래스 찾아보면 다 있어. 가져다 쓰기만 해. 근데 이제 숙제 같은 뭐 목적으로 자기가 직접 구현하게 하는 경우들도 많죠. 아무래도 귀찮아요. So that's a bit of preview for the next few chapters. Why in some cases we prefer a pointer-based implementations. Changing the length of the 1D array. So far we're just dealing with the 1D arrays. What does it mean to change the length of the array? Expensive operations, extra operations. So you copy. This is also operation of another big O of n, big O order big O of n. This one, what is the time complexity for adding an extra element? 이거 뭐? If I add an element at the beginning of the list, that's constant. 포인터만 갖다가 바꾸면 되니까 constant. So I already explained the first questions. In what situations do you need to do this? I don't know. Sometimes my data set has been increased a lot. I need to make it bigger. But so you like the array representation so much, you never want to change it, but you don't know how your data size will be growing. So what might be the dumbest choice that you can do? Maybe you create a size of array for 10,000 at the beginning, but you only have 10 elements to work with most of the time. That will be you're wasting another 900,000 something. You're wasting 99% of the memory. How can you change the length of the one-dimensional array? Like this. Or some crazy ideas. I don't know, you can add a pointer to the next one. Any dumbest ideas that you can have that you can try. Read 5.32, C program 5.2, mostly explaining the stuff that I describe here and in more of C++ code ways. But it's not that important that whether you know the syntax or not. The basic idea is important. Read chapter 5. Read chapter 5. Each element is represented as cell, a node. I already drew this cell or node. Each node keeps explicit information about the location of other relevant node. Simply put, they know the location of your next ones. This explicit information about the location of another node is called link or pointer. To be more exact, I should draw in this way. Each node should be like this. Each node, link, and data. So, like this. Maybe A, pointer, B, pointer, C. Maybe they don't have a pointer anymore, and they should be calling null. To be more exact, this is the way it should drawing. So cell or node, pointer or link. That's the word that we're describing here. Singly linked list. 아이고, why am I have an animation? 짜증나게. I don't like this. Let L define E1 to En. That's a typical definition of a list. Linear list. Each element of EI representing a separate node. E1, E2, E3, go on. Each node has exactly one link field that is used to locate the next elements in the list. The last node, En, in this case, this one is En, but n is 3. So I can call it as E3. Last element, they don't have any next elements, so they simply call the next one, the location for next element, next pointer is null. Seems, it's a bit different from empty. It's not an empty, but something like doesn't exist. Null is the one. This structure is called chain. Chain. That's our textbook, calls it as a chain. Linked list is fine too. Singly linked list. Why do they say a singly linked list? Singly. Yeah, it's one way, one pointer. Can you create something with the 2 pointers? Doubly, I don't know, doubly, they don't call it as a doubly, but double linked list. What do you do? In the data structure, I just simply add another pointer field, private field, for example. Maybe I can point it back. Double linked list. Double linked list too. Okay, let's finish up here. Single linked list. So obviously, after this point, we will discuss the time complexity of the single linked list. How do we create them? How do you apply each operation onto this linked list? Okay, I'm gonna call out the attendance first. 출석 부르고 출석.